My name is Matthew Miller, and this is Physics Lab 2 for Physics 2211. The objective of this lab was to observe another object in the real world and observe its motion. This time we dropped an object from rest and observed it as it fell to the ground from a certain height. An object lighter than a rock was chosen to make the observation analysis easier to compute. Once again, we used Newton's second law to inform our calculations and to construct a computational model for the system. It is important to note that we will now account for the very important force of gravity and how it affects most forces in the real world. Some background info about this lab: we used Newton's second law to calculate the final velocity and final position for the ball as it moved through time. The gravity force is calculated by multiplying negative 9.8 times the mass of the object. For part of this lab, we were to calculate a drag force, which is the force that acts opposite to the relative motion of any object moving with respect to a surrounding fluid or air. The first step was to analyze the video of myself dropping a stress ball from rest with the video tracking software tracker. The axis was aligned to the path of the object, and the calibration stick was set to the known diameter of the ball. The initialization of the code was done by setting the ball's mass, the ball's position and velocity vectors, and adjusting the time delineation of the code to 0.017, which matched that of the tracker video. G was set to negative 9.8, and because we were not including drag in this simulation, we set that to 0. The while loop was calculated from calculating the net force on the ball, which was the ball's weight times negative 9.8 times j hat, and we adjusted the ball's velocity and ball's position equations to match those of Newton's second law. You can see the simulation to the right. I then compared these two models, the tracker data and the computational data, on a position versus time graph. You can see that the position for the tracker data is a little bit off than the computational data. The computational data appears to have dropped faster than the tracker data. We will review how this might have happened later. The next step was to calculate the drag force. This was done by multiplying 1/2 times the liquid or air's density times the velocity squared times the reference area of the object dropped, and multiply that by the drag coefficient. This yielded a drag force of 0.005681. I then constructed a computational model including drag. I adjusted the drag value and then adjusted the calculation for the net forces on the object as it was dropped. This included the drag force, negative b times the magnitude of the ball's velocity squared times j hat. As you can see, the computational model is to the right. I then compared all three sets of data to see which one predicted the best motion. The tracker data in blue was what was observed, and the computational data without drag in green and with drag in yellow. You can see that the position is almost the same for the computational model with drag, which is a very good prediction. We then were to examine the velocity versus time predicted by our models with and without drag. Which models, if any, predict terminal velocity? Terminal velocity is the constant speed that a freely falling object eventually reaches when the resistance of the medium through which it is falling prevents further acceleration. The model without drag force exhibits constant velocity, while the model with drag will exhibit terminal velocity given the right amount of time. So the next step was to see if an object was thrown down with an initial velocity. Would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? The object with the initial velocity of -2 meters per second will reach terminal velocity much faster and will travel farther than the object dropped from rest, but both will achieve terminal velocity, but at different rates. Thank you.